Demand paging is a lazy memory allocation technique used by Linux for better memory utilization and performance. You can learn this concept in any operating systems book, but here in this video you will see that in action. I'll use all sorts of Linux tools to demonstrate the concepts you learn. This practical knowledge is the real requirement in tech industry. In the first section, I will explain the concept demand paging. In the second section, I will run the code, pause it at different stages and examine whether a physical page is allocated. Additional to demand paging, you will learn how to see memory mapping information in the proc file system. I'll teach you how to use ps command to see page faults. Also, I'll introduce a tool that prints page table information of a running process. Let's take this simple C program. At this line, the code allocates memory. The expectation is this allocation request will be satisfied by Linux kernel. But under the hood, Linux allocates no memory for this request. It will just add an entry in the page table as it is request to allocate heap memory. Linux will mark those pages with read and write but no execution permission. Additional to permission bits, page table has other control bits too. Among those, the present bit will be set to 0 as these pages are not physically present. How does the program work without the necessary memory being allocated? We'll see that by continuing the execution. Next line is memsetting that allocated memory region. As the virtual address of the memory is hex 5000, the program tries initialize the region with constant. You can see that there is no corresponding physical frame against that address, so it will result in a page fault. This page fault will be captured by the Linux kernel. It will check the permission bits and the operation is a legitimate write operation. Now the kernel will find an unused page frame in the physical memory and put it against the address hex 5000. As the memory page allocation happens when the memory is really needed or in demand, this is called as demand paging. In Linux, proc PID map will have the virtual memory mapping information of a process. This is the memory map of the cat process. We'll use this file to get the heap memory section of our program. Next, with the ps command, you can find how many page faults are caused by a process. This command prints how many minor page faults incurred by the init process with PID 1. Here is a nice open source tool, pagemap, that will print page table information of a memory segment of a process. All you have to do is clone the project and run the make command. Now you can use the pagemap binary to print page table information. With all the tools in place, we need to instrument the code as follows to examine its status at various stages. I have added a getChar immediately after the malloc. Let's see the heap region of the process and feed that to pagemap. As you're seeing, only 2 pages are backed up by physical frames. Also, let's see the number of minor faults caused by this process so far. Let's proceed to memset. After that, we see the pagemap. You can see that additionally one more page got allocated. Also, the number of minor page faults got incremented by 1. As I told initially, malloc doesn't allocate any memory at all. All the memory allocation happens only when the demand arises. Hope this video was insightful and you enjoyed it. You can find link to the code in the description. Nothing will improve your understanding like a hands-on. So please download the code and try out different ideas and share your experience in the comments below. Thank you for watching and please subscribe to our channel for better learning.